Hello everybody, my name is eMoney SD. Welcome back to my YouTube channel. Today we're going to cover the second half of chapter 16. We're going to finish it up today. Now today we're going to talk about pericyclic reactions. A pericyclic reaction is the type of organic reaction where the transition state of the molecule has a cyclic geometry with no charge during transition state either. These reactions can be classified into three major groups: cycloaddition reactions, electrocyclic reactions, and sigmatropic rearrangements. For each of these reactions, they have the following common features. These are characteristics of all pericyclic reactions. Four really important points that make pericyclic reactions. The first is that the reaction proceeds via a concerted process. This means that all changes in bonding occur in a single step, and as a result, the reaction mechanism is going to have no intermediates. All right. Second feature that is common for all pericyclic reaction is the reaction involves a ring of electrons moving around in a closed loop. 3, the reaction occurs through a cyclic transition state. And last, the polarity of the solvent for these reactions generally does not have a large impact on the rate or yield of the reaction. And this suggests that the transition state bears very little, if any, partial charges. Now, the three major types of pericyclic reactions really differ in terms of the number and type of bonds that are broken and formed. For example, in a cycloaddition reaction, the 2 pi bonds are going to be converted into 2 sigma bonds. So you lose 2 pi bonds, you form 2 sigma bonds, resulting in the addition of 2 reactants to form a ring. In an electrocyclic reaction, 1 pi bond is converted into 1 sigma bond. So you lose a pi bond, you form a new sigma bond. This effectively joins the ends of 1 reactant to form a ring. In a sigmatropic rearrangement, 1 sigma bond is formed at the expense of another, and the pi bonds simply change locations. So you're not really forming any new pi or sigma bonds. You're keeping the same number of sigma and pi bonds. It's simply more of a rearrangement, hence the name. All right, so let's take this information. All right, take a look at this picture of example of a cycloaddition. Look at that. You're starting off with 3 total pi bonds. You lose 2 of them at the end in your product, but you form 2 new sigma bonds that were not there. For electrocyclic reactions, reactions, you're starting off with 3 pi bonds. You lose 1, and in its place is replaced by a sigma bond. Sigmatropic rearrangement, you have 2, you end up with 2, and the same goes for the sigma bond. Same in the beginning for the reactants, same in the end. So we can go ahead and fill out the chart accordingly, right? Your reactants for your cycloaddition, you have 3 pi bonds starting, all right, but you only end up with 1, right? So minus 2 pi bonds. For electrocyclic, you start off with 3 pi bonds, you end up with 2, all right. And for sigmatropic rearrangement, you start off with 2, you end up with 2. There is no change here. All right, so you got to keep that in mind when we're working through these 3 reactions. Our real focus for this session specifically is we're going to be doing a lot of cycloaddition, all right, and a little bit of sigmatropic. I mean, the main thing that we will be covering here is Diels-Alder reaction, and that falls under the cycloaddition. So keep these patterns in mind so you know how to distinguish between the 3 pericyclic reactions. But with that, now what we really want to talk about, the highlight of this chapter, is the Diels-Alder reaction. It's an incredibly useful pericyclic reaction. It is specifically, like we said, a cycloaddition type of pericyclic reaction. The Diels-Alder reaction is a chemical reaction between a conjugated diene and an alkene, and this alkene can be substituted or not. Now, the Diels-Alder reaction is also called the 4+2 cycloaddition because the reaction takes place between 2 different pi systems. One is associated with 4 atoms, like you see here, while the other is associated with 2 atoms, like you see here. Now, the product of a Diels-Alder reaction is this substituted cyclohexene. As in the case for all pericyclic reaction, the Diels-Alder reaction is a concerted process, right? That means it happens in one step, and there's only one transition state, like you see here, all right, that is usually not charged. Now, let's discuss some of the thermodynamic consideration for the Diels-Alder reaction. The Diels-Alder reaction is a exothermic one that is favored at moderate temperatures, okay? If the temperature gets too high, however, then the reactant is favored over the product. What you get here is this thing termed retro Diels-Alder reaction. And the reason for this relationship obviously has to do a lot with Gibbs free energy. All right, so let's take a closer look here. What is our Gibbs free energy? All right, remember, if we get a negative Gibbs free energy, that means our reaction is favorable, and a positive Gibbs free energy means it's not, right? So if our delta H, if our enthalpy is exothermic, that means our delta H term is negative. All right, our entropy is also here negative, all right, because you're not really, you're starting off with two molecules, right? Your diene, your diene, and what we'll cover to be called our dienophile. All right, you're starting off with two molecules and ending up with one. Now, if you remember from Organic Chemistry 1, when we covered Chapter 6, where we talked about thermodynamics and kinetics, all right, we talked about entropy. All right, positive entropy is when you start off with less molecules and end up with more in a reaction. All right, with Diels-Alder, you have two reactants, you end up with one product. All right, you start off with more reactants than you end up with products, and so then our entropy is negative. If our entropy is negative and it's being multiplied by a negative temperature, then this whole term right here is positive, whereas our enthalpy term is exothermic, so it's negative. In order to accommodate for the fact that our Gibbs free energy should be negative, we got to keep that temperature low enough so that our enthalpy term prevails and our Gibbs free energy is negative, which is why Diels-Alder reactions are favored at low temperatures. You get high temperatures and then your reactants are favored, and you get that retro Diels-Alder reaction. So that's a good thing to keep in mind. Also, now we've said that the starting material for a Diels-Alder reaction is a diene, right? This conjugated diene. And the compound that reacts with this diene is called a dienophile. All right, the Diels-Alder reaction occurs when the diene, all right, our condition for the diene is that it must be a cis diene. All right, it has to be a cis chain configuration. All right, so that is our condition for a Diels-Alder reaction in regards to the diene. It has to be in a cis configuration. Now we're going to discuss how a Diels-Alder reaction proceeds, knowing that our diene has to be an a cis conformation. All right, we're going to discuss how a Diels-Alder reaction proceeds when the dienophile, all right, takes on certain substituents or configuration, all right, considering that the diene is in a cis chain configuration, all right? That's where we're going to start this discussion, all right? When the dienophile does not contain any substituents, all right, so you have your diene that looks like this and your dienophile that just looks like this with no substituents, all right, the reaction exhibits a very large activation energy. That means this reaction is going to proceed slowly. Now, you might say, okay, well, we can increase the temperature to lower the activation energy. We learned that in Organic Chemistry 1. Well, if the temperature is raised too much to overcome the energy barrier, then what you get is that the starting materials are now favored over the products, right? Because we got to keep in mind what we just discussed in regards to Gibbs free energy. You might think increasing the temperature will help you overcome the energy barrier, but what actually happens is that the starting materials are now favored over the products and the resulting yield is low. Now, a Diels-Alder reaction will proceed more rapidly and with much, much higher yield when the dienophile has a electron withdrawing substituent, such as a carbonyl group. All right, when the dienophile, all right, is a 1,2 disubstituted alkene, for example, the reaction proceeds with stereospecificity. All right, so that's something to keep in mind. All right, when your dienophile has no substituents, all right, the reaction's gonna occur very slowly. All right, now if your dienophile has one substituent, all right, some sort of electron withdrawing group, like say a carbonyl, all right, the reaction will proceed quickly. All right, now the other thing to keep in mind is what if your dienophile has two groups attached to it? All right, some X and another X. All right, in this case, all right, we gotta think about the fact that the reaction proceeds with stereospecificity. All right, specifically, a cis alkene, a cis dienophile, is gonna produce a cis disubstituted ring. All right, where both of the groups are either both on wedges or both on dashes. All right, now if your dienophile is disubstituted but it's in a trans configuration, all right, it's gonna produce a trans disubstituted ring. All right, so that's what you keep in mind when your dienophile, when your alkene is disubstituted. All right, you got to think in terms of stereospecificity. All right, a cis alkene will produce a cis disubstituted ring. Easy. All right, a trans alkene is going to produce a trans disubstituted ring. Pretty straightforward. All right, now we are going to discuss how a Diels-Alder reaction proceeds when the dienophile takes on certain substituents or configurations, considering that the diene is in a cis ring configuration. All right, so what if we have a diene starting off? All right, again, it has to be cis, but now it's also in a ring instead of a chain. All right, we were looking at chain examples. Now, what if our diene is still cis? It has to be, but it's in a ring configuration. How is it going to deal with different kinds of dienophiles? All right, when cyclopentadiene, that's what this is called, is used as a starting diene, all right, what you're going to end up with as a product are these bridged bicyclic compounds. All right, these are what are obtained as a product. Why? All right, well, let's take a look here. All right, let's draw our cyclopentadiene. Here's our double bonds. All right, and it's gonna react with a dienophile, right? This part of the ring is gonna sort of, and you can think of it a little less scientifically. It's kind of like moving up to get out of the way. All right, and if it moves up to get out of the way, it's gonna look something like this to get out of the way, so that this may react together to form that ring. All right, but this part is still there. It's not gone. That carbon right there doesn't go away. It just gets out of the way so that the diene and the dienophile can react. And so a consequence of that are these bridged bicyclic compounds. They're obtained as products. In such a case, we might expect to obtain the following two products: an endo product, all right, and a exo product. All right, so in one cycloadduct, the electron withdrawing substituents are gonna occupy the endo positions. All right, and in the other cycloadduct, the substituents are gonna occupy an exo position. Now, the endo positions are syn to the larger bridge, all right, while the exo positions are anti to the larger bridge. Which one is more favorable? The endo product is preferred because there is more favorable interactions that happens between the electron withdrawing substituents and the pi bonds. All right, these are further away from, say, the bridge or the double bond as opposed to the exo product. All right, so your endo product is preferred. All right, now for a Diels-Alder reaction, all right, there's only one possible regiochemical outcome if either the diene or the dienophile is symmetrical, as we've seen so far. All right, and we're going to do examples for what we just covered right here before we get into the part of what to do when both the diene and the dienophile, or one or the other, is unsymmetrical. All right, so that's coming up, but what we really want to do now is a couple of practice problems. All right, so we're going to go ahead, we're going to do some practice problems here. All right, predict the products for each of the following reactions. Okay, so we have we have our conjugated diene, all right, and then we have our dienophile. All right, now the dienophile here, all right, let's notice, all right, it's di substituted. The dienophile is di substituted. All right, our diene is conjugated, it's a cis chain. Fantastic. Our dienophile, and we're doing A here, our dienophile, all right, is di substituted, and look at them, they're both on the same side of the double bond, so they are cis. All right, we're dealing with a cis chain diene, all right, and a di substituted cis dienophile. All right, we talked about this. We take a cis diene chain and we react it with a dienophile that's cis. All right, we got to make sure that our ring structure at the end has to be di substituted, and the two functional groups have to be on the same side. So that means we form a ring, all right, with one pi bond, because in our Diels-Alder reaction, it's cycloaddition. All right, so instead of having 3 total pi bonds that you start off with, all right, you're only going to end up with 1. And then you have your substituents, and they're cis, so they're going to be both on the same phase. All right, they're going to both be on, say, wedges, for example. All right, and then we can add them right here. I'm not very good at drawing, but there we go. So that's what our product looks like. All right, fantastic, very easy. Let's do B. All right, again, we have a diene. It's cis, and it's in a chain, right, not a ring. All right, and it's going to react with this dienophile that is di-substituted, all right, and they're both on the same side of the double bond, so it's cis. Fantastic. All right, we do the same thing. We draw our ring structure first. It'll always look like this. All right, our 3 total pi bonds turn into 1. That is the consequence of cycloaddition. All right, and then our carboxylate groups are both going to be cis to each other, so on the same kind of phase. So they'll both be on wedges. And then we could just write our carboxylate group right there. All right, let's do that last one, C. All right, again, we have our diene. All right, cis chain, fantastic. All right, and our dienophile here is di-substituted. All right, it's di-substituted. We could redraw this so you can see it better. Here's our dienophile. All right, we have one group on one side of the double bond, as you can see here, and the other group on the other side. All right, what this means is we actually have a di-substituted trans dienophile. All right, so that means when we draw our ring after the diene and the dienophile, react together, our substituents that were on our dienophile actually have to be on opposite wedge dash configuration. All right, so that is exactly what we're going to draw here for our final product. All right, so oops. All right, so something like this, and then on a dash and something like this. Fantastic. All right, so that's how we're going to approach these kinds of problems. Fantastic. Now, let's do a couple of these problems. All right, predict the products for these following reactions. All right, again, we're going to look at A. All right, we have our diene. All right, it's in our cis configuration, exactly what we need, because that's the only way this Diels-Alder reaction is going to proceed. But what we have now is a cyclic diene. All right, it's in a ring structure. We know what that means. Our products are going to be bicyclic compounds. All right, now our dienophile, all right, our dienophile is going to be, all right, it's di-substituted, and they're both on the same side of the double bond, so it's cis. Fantastic. So we're going to go ahead and we're going to draw the product for this. All right, so we're going to draw our bicyclic compound. All right, I'm so sorry. I'm not very good at drawing these, but I'm going to try my best. All right, here's our bicyclic compound. We have our double bond right here. All right, this carbon is what forms the top of this, right? Because it kind of tries to get out of the way so that this diene, this part of the diene and this part of the dienophile can react to form this ring right here that I tried to draw. All right, and then we draw our two substituents in the endo configuration. All right, we also get, all right, the exo products. All right, but what's our favorite product? It's our endo product. All right, let's do B now. Okay, again, we have our conjugated diene. It's in a cis configuration, thank God. All right, and it's also cyclic. So once again, for our product, we have to think bicyclic compound. All right, bicyclic compound. And let's get a different color to draw this. All right, so what this means is we get a bicyclic compound. Let's draw out the sketch of what a bicyclic compound looks like. Now, what we have here is an oxygen. All right, so that's what we have to draw at the top here. This is an oxygen, no longer a carbon that's getting out of the way so that the diene, the conjugated diene part of the ring can react with our dienophile. It's now an oxygen, so you got to make sure you draw that appropriately. All right, now our dienophile, is trans here. All right, it's trans, so they can't both be in the same phase. All right, so that means we can't draw our endo product for this with a C in here and a C in here and then say we have also our exo product. All right, what we have instead here is one cyanide group in the exo position and one in the endo, because our dienophile is trans. They're not going to both be in the same phase, like they'll both be on wedges or on dashes, or in other words, both be taking a downward position or upward position, or endo or exo, but instead one will be in what you would say your exo position and one in your endo. All right, I will leave C for you to figure out. All right, and with that being said, we're going to move into the second part, right? We said for our Diels-Alder reaction, right, we stated that there's only one possible regiochemical outcome if either the diene or the dienophile is symmetrical, as we have seen so far. However, if both the diene and the dienophile are unsymmetrical, then there are two possible regiochemical outcomes. All right, kind of like what we see in this figure right here. This is unsymmetrical and this is unsymmetrical. All right, there are two products as a consequence of that. They are constitutional isomers. One of these isomers is favored over the other, so the reaction is said to be regioselective. Now, the major product can generally be predicted by considering the charge distribution in both the diene and the dienophile. And to do this, what you want to do is draw the resonance form of each, then line them up to draw the appropriate product. This is how you will figure out which one of these two is actually your major product and which one is not. All right, so let's look at this example. All right, this example pretty much takes, all right, our diene, as you see here. This is our diene. All right, and it draws the resonance form of the diene, right? Our oxygen has lone pairs that can be dumped here to form a double bond. But if we form a double bond there, if we make a bond, we have to break a bond, all right? And so now we have this double bond here that causes a positive charge at the oxygen and a negative charge at this further carbon here, all right? This is the resonance form of our diene. All right, we can do the same with our dienophile. Let's draw the resonance form. This double bond can move over here. All right, but if we do that, we have to break this double bond and dump the electrons on the oxygen. Now, the oxygen has a negative charge on the and this furthest carbon has a positive charge. Now what we want to do as step 2 is align the molecules by placing oppositely charged carbons next to each other. All right, oppositely charged carbons. In our diene, we had a negative carbon here. All right, we want to line it up with our positive charge that we have on the carbon from our dienophile. If we line them up like so, with a negative carbon facing a positive carbon. All right, now we can go ahead and draw our product as such. All right, now we know how to line up our diene and our dienophile. So we go back to the original way that our diene looks like and line it up with the way that our original dienophile looks like, not the resonance form anymore, since we figured out how to line them up. And then what we can do is draw them in the correct alignment. All right, and that's how we know what our major product is. All right, so with that being said, what we can do is kind of put all of these pieces together in regards to how to approach our diene and dienophile configurations in order to always be able to approach these kinds of problems appropriately. All right, now if our diene is unsubstituted and our dienophile is unsubstituted, you're just going to proceed with no worries. It will be a slow reaction, but you know what your product looks like. Now, if your diene is unsubstituted, but your dienophile is monosubstituted, again, you just proceed with no worries. There's nothing to keep in mind here in regards to regioselective or stereospecific or yada, 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 right? Now, if your diene is unsubstituted, but your dienophile is disubstituted, then you just got to make sure you label them. Is your disubstituted dienophile cis? If it is, a lead to a cis disubstituted ring, and if it's trans, a lead to a trans disubstituted ring. All right, now if you're dealing with a diene that is cyclic, all right, and then you're in a disubstituted dienophile, all right, then you just have to remember, all right, for cis, you have your endo preference, all right, that is your preferred product for a cyclic diene and a disubstituted dienophile. And if it's trans, then you're gonna get this as your product with one position in the what you would have thought your exo position and your endo. All right, and then if your diene is monosubstituted and your dienophile is also monosubstituted, right? They're unsymmetrical here. All right, then you have to consider regioselectivity, where you draw the resonance structures of both, line them up to get your major product. And with that being said, what we can do now are a couple practice problems for this last part. So let's go ahead and let's do A. Actually, we did A for the example, I think. Was this exactly like our example? Let me check. We don't want to do that again. It's slightly different, so we'll do it, all right? So what we're going to do is we're going to take our diene. Here's our diene. And we're going to draw the resonance form of this diene. All right, so when we're doing that, we can take the lone pairs that are on oxygen, dump them here to form a double bond. All right, then what we have to do is move this double bond here and then break this double bond and have it dump its electrons there. So what we get as a resonance form for our diene, we have a positive charge on our oxygen, all right? And then our negative charge is here at this carbon. Then what we can do is look at our dienophile, all right? This is what our dienophile looks like. Let me draw this better. Draw out all the bonds. All right, fantastic. What we can do here to draw the resonance form, all right, this double bond can move here, all right, and then we can break this double bond and dump the electrons on the oxygen. All right, so what we get as a resonance form for this structure is an oxygen with a negative charge, and here's our positive carbon. Fantastic. Now, all we have to do is line up the negative carbon with the positive carbon, and this is how we will do it. Here's our diene. All right, here's our diene. Here's the negative carbon right here. We're going to line it up with this positive carbon that we got from our dienophile. All right, and now they're lined up. All right, now what we can do, now that we've known how exactly to line this up, we can draw them back in their original form. All right, so what does our diene look like before we drew the resonance form of it? It looked like this, keeping it all aligned. And what did our dienophile look like before we drew the resonance form? Draw it in the same form that we have here where we aligned everything. All right, boom, just like this. All right, and now we can form our major product. All right, and we know exactly where to attach everything. Here's our methoxide group. All right, and here's our aldehyde group, and this is how they will line up to form the major product. All right, I'm going to let B be something you try to do, and I'll post the answers. All right, now this last topic of discussion for the subject is a few points that I want to make. All right, now in terms of molecular orbital theory, a Diels-Alder reaction is accomplished when the HOMO of one compound interacts with the LUMO of another. All right, we can see this. We can see this in this example right here. All right, here's our diene, and here's our dienophile. All right, we have 4 electrons that we're dealing with here. So if we fill them up, all right, all right, here's our HOMO from the diene. All right, and if we fill this up, the dienophile, and we take the LUMO of the dienophile, all right, and we take what they molecular orbitals look like for the HOMO of our diene, which looks like this, right? It has this one node, so positive, positive, minus, minus. All right, and we take the LUMO of our dienophile, all right, which also has one node, positive, minus, minus, positive. All right, and we line them up, and they line up where these look exactly alike and these look exactly alike. All right, symmetry allowed. All right, and we have the smallest HOMO-LUMO gap. All right, then a Diels-Alder reaction is possible between this diene and this dienophile. All right, now if this was ethylene and you took the HOMO for one, which would look like this, positive, positive, no nodes, and you took the LUMO for the other ethylene, this is the HOMO for the first one, and the LUMO for the next one, which by the way has a node. All right, look how these don't line up exactly like they did here. All right, and so you can use molecular orbital theory and the way that the HOMO of one compound interacts with the LUMO of another to see if this reaction will proceed or not. This is kind of like the background information of our Diels-Alder reaction. All right, and as a last topic for this discussion, we're going to talk about sigmatropic pericyclic reactions. All right, it's fairly easy. There are 2 main ones, all right, that fall under this, but let's define it. A sigmatropic rearrangement is a pericyclic reaction in which one sigma bond is formed at the expense of another. And in this process, the pi bonds simply change their locations. All right, there are 2 different sigmatropic reactions we're going to cover. The first is our Cope rearrangement. All right, it's a 3,3 sigmatropic rearrangement. It's called our Cope rearrangement. And what happens is all 6 atoms of the cyclic transition state are carbon atoms. All right, we're just dealing with a sigmatropic rearrangement with just carbons. All right, the oxygen analog of a Cope rearrangement is this thing called the Claisen rearrangement. And the same thing happens where really pretty much you're just moving around some of the pi bonds, all right, and forming new sigma bonds, but not creating anything new in terms of the number of pi bonds and the number of sigma bonds. All right. Now, in these next 2 slides, I just made this because I thought it would be helpful to summarize our whole chapter 16 in just 2 pages. The first page is what we covered in the first part of chapter 16 as a friendly reminder, and this is just a flow chart for pericyclic reactions, where, of course, the main topic for this chapter is the Diels-Alder reaction, which falls under the cycloaddition pericyclic reaction. And you can keep these as further notes, of course. I hope this was helpful. Let me know if you have any questions or if there's any topic you want me to go into more detail or you want more practice problems of, and I'm always more than happy to do that. Other than that, happy studying and have a great day.